All right, looks like we are live here on Standing for Truth. I've got my nemesis here, the evolutionist nemesis, Grayson. We've done a couple of formal debates over the last month that have equaled about 6 hours worth of formal debate. So what we're going to do now is start a series of conversations. Me being a creationist, Grayson being an evolutionist, and one day a creationist. So, and he'd probably say me one day an evolutionist. So that's why we're going to have these conversations, though, because they're important. And there's just so many important points and topics that we really only touched upon, as Grayson would probably agree, in our 6 hours worth of formal debate. Great to see those debates getting a lot of feedback. I've had a lot of comments, messages saying that that's one of people's favorite debates in terms of how technical and comprehensive it was on ancestry. So I'm a firm believer that the best way to determine ancestry or answer this question of ancestry, universal or separate, is through genetics. It's genes, traits, and genetics that are inherited sperm and egg, not a rock, not geography, not a bone, but genes and traits. And so I strongly believe that it's in the world of genetics that we can solve this controversy, essentially. So what we're going to do is basically a series. We're going to try and keep them an hour long, so we don't burn ourselves out. Grayson and I, we want to do a lot of these chats. We'll do one on ERVs. We'll do one on chromosome 2 fusion. We'll do one on junk DNA. We're gonna touch them all, because we don't want to be an echo chamber where it's just, either a bunch of creationists in a room or a bunch of evolutionists in the room, telling each other, wow, you're so good, great job, patting each other on the backs. No, we actually want to get together and in a professional and sophisticated manner have these discussions with those we disagree with. So Grayson, thanks for doing this. Before I present my first point in terms of what this topic is, which is specifically genetic diversity out of Africa, out of Middle East, and how this relates to genetics specifically. So, but Grayson, thanks for doing this. I know it's late for you. Did you want to say a couple words in terms of introduction? I know you're working on getting a YouTube channel soon as well, which I'm sure your fans will be excited about. So anyways, how you doing tonight?
Well, like you said, it's a little bit past my bedtime, but I'll try to, be my same peppy self. So other than that, I think we should just get into it so we have more time to discuss.
Okay, let's get right into it. Grayson, thank you so much. Question from Jeremy Nolan says, is this live? Yes, it is. We're going to do these live. For the most part, we discuss, should we record it or live? And you know what? Even though it's late, and so we're not going to get as many people as we would in the afternoon, there are people on different time zones. And so at least they have something to enjoy. Okay, so what I want to talk about, Grayson, and we talked about it briefly in our first debate, but I felt we did not get the opportunity to really expand on it and touch on it in great detail. And that's why we're going to touch on it here for an hour. So I think one strong argument for the separate ancestry model, which would basically say that humans are specially created, separate from any other form of life. That includes your great apes, which you would call non-human apes. And therefore, that would obviously include whales and pine trees. Universal common ancestry would say that humans fit with primates, fit with mammals, and basically mammals and plants are related, whales and pine trees kind of thing, okay? So I like to stick as close to home as possible. So rather than showing you why I believe the evidence suggests whales and pine trees aren't related, I like to argue for reasons why humans and chimpanzees aren't related. Because I think we could agree if humans and chimpanzees aren't related, well, then humans and strawberries probably aren't related, right? Okay, so a strong line of evidence, which is also a simple line of evidence, is levels of diversity. And what I mean by that is, and I believe we could agree, that mutations add diversity, because mutations are adding something that was not previously there. Now, the evolutionary model would suggest or explain nearly all genetic variation as being the result of mutations over time. Okay. But what we find in terms of the genetic variation in humans is that humans have very low genetic diversity, very low genetic variation. Now, according to the biblical model, if we were to start with two people, Adam and Eve, well, right off the bat, that would restrict levels of diversity. Okay. And so what we find, and the evolutionary community was caught off guard with it, is that humans have incredibly low variation. This goes for your autosomal DNA, Y chromosome DNA, mitochondrial DNA, just overall low genetic variation. So here's where I want to sum up my argument. Why this is important is because to us as biblical creationists, this is what we'd expect. Right? God creates two people, Adam and Eve. Right off the bat, that restricts levels of genetic diversity. It's been about 6,000 years since the creation event. Okay, that's what we would expect. Sounds good, looks good. We have nothing really to explain. But the evolutionary model, they propose that humans essentially originated, 200,000 years ago in Africa somewhere. Before that, you had Erectus on the globe for, a million years or more. Habilis, Australopithecine-like ancestors. So essentially you have millions of years of mutations accumulating and adding diversity to the genome. So the question is, for the evolutionist, why do humans have such low levels of genetic variation when, if deep time evolution were true, they should have high levels of genetic diversity? And so I would say the levels of genetic variation that we see in humans is better explained by the separate ancestry model than the universal common ancestry model. And so that's my argument. Those are the points I want to focus on for this specific podcast. Grayson, go ahead, take as much time as you need to kind of give your thoughts on that and maybe critique it a little bit.
All right. Well, I only really need 2 words because I think you already kind of know what I'm going to say. Population bottleneck. That would be, we see population bottlenecks. We can record the effects that they have on genetics, and we see that they decrease genetic diversity.
Oh man, you barely gave me enough time to take a breather. Just so yeah, bottlenecks and small population, like you said, right? Okay. So I've had many discussions with many different evolutionists on this topic. Okay. You would say, and so I don't want to just argue against them. I want to argue against what you believe, since there are different beliefs in terms of this. Some would say that there was 2 bottlenecks. Some would say that there was multiple a few bottlenecks, even including a bottleneck with Erectus in Africa. Some would say, this bottleneck, the main one was 70,000 years ago. Others would say 200,000 years ago. So I guess my question to you, my first question is, how many bottlenecks do you believe humans have experienced and when?
All right. Well, probably hundreds. Every time you have an island chain, you're going to have a bottleneck. There's going to be a founder effect. But if you're talking about bottlenecks that are shared by the whole of mankind, then the main one is going to be back in Africa. So the 70,000 year one that you're talking about is the out of Africa event, but that's not shared by people living in Africa today. So the population bottleneck that explains the genetic diversity that we see among the entire human species is the one going back to Africa.
Yeah. So what would you say was the major bottleneck that reduced levels of heterozygosity? For the audience sake, heterozygosity just means a state of DNA diversity where you'd have, in terms of alleles and basic genetics, capital A, lowercase a, capital B, lowercase b, you're heterozygous at those genetic loci. If you're homozygous, you'd be capital A, capital A, capital B, capital B. There's no diversity there. It's basically one gene and it's the same alleles. There's no variation there. So which time period and which specific bottleneck, since we see humans as a whole, so we can agree that there's been many different bottlenecks where subpopulations, right, Grayson, went into a bottleneck, became isolated, experienced inbreeding, and as a result, levels of homozygosity were increased, levels of heterozygosity were decreased. But it's the human population as a whole, the human species, I guess you could say, that has low variation. So where do you put the major bottleneck? that reduced human variation as a whole?
Yeah, probably between around 100,000 to 200,000 years ago. I mean, I don't have an exact date for it. I think that they've used estimates to like of the genetic diversity and like measuring genomes to guess it was, the human population might have gotten down to, even potentially less than 10,000 individuals based on the level of genetic diversity that we see today.
Okay, I'm just writing what you're saying.
But that's
So
for the main human-wide.
main one, right?
Yeah,
And then there's been smaller ones since, you're saying.
yeah, there's countless smaller ones. A good example is the peopling of the Americas, so North and South America. All of the Native Americans show very little genetic diversity, even when compared to the whole, like humanity as a whole. So, like looking at different subgroups, actually, we see patterns in the genetic diversity that correspond to bottlenecks and founder events, which are like the principles at work behind the population genetics of founders events are very well known and are studied in like lots of different animal models. So we know how this affects population genetics.
Okay, so you putting the bottleneck 200,000 years ago, you'd put it into Africa. Now, is this Homo sapiens, or would you say Homo erectus, or in the intermediate stage?
Yeah, this should be Homo sapiens.
Okay, so Homo sapiens in Africa, roughly 200,000 years ago, possibly down to, so what I've read in the literature, which I've conveyed in my book, Special Creation, is some say 2,000, some say 10,000, others say up to 30,000. There's really no way to know, even if evolution were true, just to kind of steel man the position, argue from that position, because I think, as you iterated, they're basing their number on genetic variation, right? What we see today in humans, this is how low it is. And so, how long, how many people would it take basically to account for that? So I guess my next question would be, so in Africa, you have a bottleneck where the human population's reduced to, let's say between 2 and 10,000, maybe as much as 30,000. How long now is this bottleneck? In order to reduce the necessary levels of heterozygosity and increase levels of homozygosity, we both agree, I think, that going into the bottleneck, so pre-bottleneck, your human species at the time, Homo sapiens, they would have had high levels of genetic diversity. Okay. So in order to reduce those levels of genetic diversity, I think we would both agree as well that it wouldn't just be a 1-generation bottleneck, a 2-generation bottleneck. It'd have to be more than that. So what number would you put on it if you had one, Grayson?
Yeah, honestly, I wouldn't be able to comment on that with any authority. I've got, not even a guess as to what would be the amount of time. I'm sure that there has been research that's been done on this. But in terms of, the length of the reduction in population and like how long it took the population to bounce back to healthier levels, I really haven't, I haven't read those papers myself, so I wouldn't be able to comment on that.
And that's fine, because there's not much, and I've searched far and wide. There's not much in terms of a confident answer on that, right? Some would say maybe 1,000 years, maybe 10,000 years. It depends how heterozygous that population was at the time. But I would argue, if you have Australopithecine-like ancestors evolving for millions of years, adding mutations every single generation, therefore adding diversity, up to, let's say, Homo habilis, you're transitional, and then eventually Homo erectus, who essentially lives on the globe for 1 million years. Some would say that there's been a couple out of Africa where you have erectus. Tell me if this is what you believe. Erectus leaving Africa and independently evolving on other continents into some of your, quote unquote, pre-humans like Floresiensis, Naledi. Some would even say Neanderthalensis, Heidelbergensis. What's your position on that? Do you believe in multiple out of Africas, one with erectus, or yeah, go ahead.
Yeah, definitely multiple out of Africas. Before Homo sapiens arrived on the scene, there were other kind of humans like Homo erectus, like you listed, is probably the best candidate for the first major out of Africa. They're the first human species that we see in the fossil record that could run long distance and could throw objects with precision, which are the two things that physically humans do better than any other animals. So they'd be very equipped to migrate and be able to hunt game in a tremendous number of different environments. So the in terms of what they differentiated into, like Floresiensis is one, Homo Neanderthals, so like Homo neanderthalensis, the Neanderthals in Europe, and then also the Denisovans in Asia, which are, for people that are not familiar, they're kind of like they're kind of similar to Neanderthal in your conception, but they're sort of the Asiatic version. So actually, like Denisovans and Neanderthals are a little bit more closely related genetically to each other than they are to Homo sapiens. So those are like the big groups that would be coming from out of the Africa movement. Like groups like Homo naledi and Heidelbergensis, those are mostly still within Africa.
Okay. So when you would look to something like the first one you mentioned, Homo floresiensis, for the audience, that's Hobbit. And they were discovered on the island of Flores, and they were shown to have, they were dwarfed, essentially. Insular or island dwarfism. They had evidence for reductive evolution, small body size, small brain size. And there's some that would say, and I wonder if you would say this, essentially Erectus, where at least Erectus had some intelligence, some sophistication, like you were saying, was able to raft onto that island, and basically, due to the effects of being isolated on an island, evolved, or I would say devolved into Hobbit. Would you more or less say that that would be the position you'd hold?
Yeah, I wouldn't use the word devolve like
Right.
you kind of called out there, but yeah, I mean, we see, Homo erectus spreading throughout the globe and differentiating into all kinds. Island dwarfism is a known condition that we observe. So, yeah, I mean, even on that island, we actually find dwarf elephants coexisting
Right.
with Homo floresiensis. So there's another example of island dwarfism. So I think that this is all well within line of what we would expect from the genetics and the fossil record. So,
okay, so my next question would be, and I appreciate these responses, it's really helpful for me, since again, there is a lot of in-house debate, even within paleoanthropology, where some would have differing views, whether it's a multi-regional hypothesis out of, yeah, go ahead.
so I think everything that I've said so far is pretty well within the consensus within the scientific community. I don't think I don't think we've touched on any topics where there's like a large amount of debate and back and forth in the consensus.
I would say one major debate on something you said was the nature of floresiensis. So some would say that it was an Australopithecine that actually rafted its way to the island and then evolved into floresiensis. Others would say it was Erectus, and then from Erectus you get floresiensis. So that's kind of one of the major in-house debates. I know.
I will grant you that one. We do not have the DNA for Homo floresiensis like we have for Denisovans and Neanderthals to compare. So there is, I think I have heard like the debate about Australopithecus or Homo, but as you can tell by the name Homo floresiensis, it's grouped within the hominids as a
Right.
so that is kind of still the consensus. But you're right, there is a minority dissenting opinion within the community.
So my next question would be then, if we have a couple of out of Africa events where Erectus leaves, independently evolves into these different hominids or pre-human types. In Africa, you still have the main, you could say, parent population of Erectus, adding mutations every generation. Let's say their generation time was roughly 20 to 30 years. Every year, adding levels of diversity. Okay. How many years do you believe from, let's say, Erectus to Homo sapiens to the massive bottleneck in Africa? How many years roughly? Could you put a number on it?
Yeah, I don't know about what the years would be on like the out of Africa for Homo erectus, but like evolution of like Homo sapiens is, kind of around 300,000 years ago, give or take. I mean, that's like a very rough guess. Um, so, I mean, like like you said, Homo erectus has been around for, you know, a million or more years. So there's like a pretty wide, age difference there.
So your answers have been helpful, basically, for me to now maybe lay out what I believe is the major issue with this. Okay. So if we have, and there's going to be two major problems, and I'd be curious how you address them. But let me, Bubblegum Gun says, go to sleep, weirdos. We don't believe in sleep. We've evolved past sleep. So, anyways, if you have in Africa, you have generations after generations of mutations adding diversity. And then you have this massive population bottleneck. That means you have, going into this bottleneck, a population that is well heterozygous. Okay, lots of heterozygous loci, you could say. So now, in order to explain the diversity today in humans, which is low, very low, okay, this is why the out of Africa bottleneck was invented. So I would say it was post hoc, ad hoc. Actually, I should ask you, just to represent you properly, do you believe, or do you know if the out of Africa bottleneck was predicted before or after levels of genetic variation in humans became known?
Yeah, I've got no clue. I know that out of Africa was predicted by Charles Darwin, but in terms of the population bottleneck, I've got
Right.
no clue on the history of that concept.
From my understanding and from my study, it was after, but I always ask who I'm discussing with because, do I know that for a fact? Not necessarily, because there's a lot of literature out there, right? That you can find hiding somewhere years and years ago where somebody predicted, you know what, there might have been a bottleneck in Africa. But as far as I currently know, and after many conversations on this, it was predicted. Wasn't predicted before, which to me then would say it's a retrodiction, but not really an impressive retrodiction. I would say it was more so post hoc, ad hoc, because, okay, we now understand that levels of genetic variation in humans is low. That wasn't expected from the evolutionary starting point or standpoint at that time. So, maybe there was a population bottleneck to explain that diversity. For the biblical creationists, right off the bat, the levels of genetic variation made sense. Two people 6,000 years ago, that automatically restricts genetic diversity. Today, low genetic diversity seems to fit like a glove. In the evolutionary model, you got a lot of genes floating around. Okay, for a million years with erectus, a lot of genes floating around. So you're going to need not just one, not just two generations to reduce levels of heterozygosity. You're going to need probably 1,000 years, maybe even up to 10,000 years to properly reduce those levels of heterozygosity. So here's where I believe the main problem is, Grayson, and take your time to explain it, is, and I'll start it this way by asking you, what are the results of inbreeding? What does inbreeding result in genetically, biologically? Go ahead.
Okay, yeah, you said a whole lot, and then you asked me a question. So
Take your
just,
time. Respond to it all. Yeah.
I'm not sure if I would agree with you that this would be like within our predictions from like
Right.
a creationist point of view. I think that there's probably too much genetic diversity for like a 6,000 year time frame, and that's why you have to have the ad hoc rescue device of created heterozygosity. That would not have been a prediction until we went out and we sampled the diversity that we see among human types. If there was only 6,000 years and using like the rates of like genetic differentiation that we observe currently, it's not enough time. That's why you have to have created heterozygosity. And then, yeah, I don't know about retrodiction or anything. I would just say that, um, and this happens all the time in science, right? When you make an observation that you're not expecting, then you come up with an explanatory model. And then you test the predictions of that model to see if it was accurate and to see if it could explain it. So I think that this is like something that we see all the time in science. I don't really see anything, we have science that makes predictions, and then we have, observations that require an explanation. So There's multiple different ways of gaining knowledge. And then finally, to answer your question, inbreeding increases homozygosity.
Okay. So essentially with inbreeding, you have deleterious alleles or mutations that have accumulated, but they're in a recessive state, essentially coming to the forefront now, because you have a greater chance at having the same allele and therefore homozygosity, more or less. You have the hidden reservoir of genetic mistakes or mutations coming to the forefront. Also, firstly, for the audience sake, let me just screen share here and just kind of show how. So perhaps the most widely cited statistic about human genetic diversity is that any two humans differ on average at 1 in 1,000 DNA base pairs. Human genetic diversity is substantially lower than so basically every single human is 99.999% the same. Okay. And you were right, inbreeding would increase levels of homozygosity, but because you have a prolonged bottleneck, right, Grayson, you'd have a lot of time, therefore, for deleterious recessive mutations to come to the forefront, leading to genetic damage, leading to disease. And so what we get in a prolonged bottleneck like that in Africa, where you have humans reduced to between 2 and 10,000, is rapid genetic degeneration and near extinction, rather than a moment in time where suddenly all people spread out into all parts of the globe, seizing dominion over the planet. So that's why I find this explanation not feasible. I find it unlikely. And that's why I would say that it is post hoc, ad hoc, because, and I'll say this and then take your time, a prolonged bottleneck like that with such severe inbreeding would lead to such significant genetic damage that it's not feasible that at some point you're going to have humans spread out in all parts of the globe as if, this is a good thing. Go ahead, Grayson.
Yeah, well, I'm not exactly sure if we've seen any evidence of like widespread inbreeding among these populations. Like you could have as long as a population is over 150 individuals, then you can pretty well survive without having any dangerous amounts of inbreeding between those individuals. And we're talking a few multiple thousands. Spread out over a geographic area, but humans are very mobile. I don't really see any reason in particular why they would be forced to participate in inbreeding and be unable to find different mates. But if you had some sort of catastrophic event that rapidly reduced the human population, that would be enough to decrease heterozygosity, to decrease genetic diversity. So I don't know how long of a process that you would have that, like, maintain that small population before you start to have a more healthy environment that nurtures more of a population expansion. And there are numerous genetic studies that have been done with like fruit flies, for example, where they massively increase the homozygosity and decrease the genetic diversity, and they kind of artificially create this situation, and you have all this genetic degradation. And then when they increase the resources and increase the population, after just a few generations, the population starts to heal and go back to a healthy state. It's still a less diverse population than it was before, but you don't have those kind of like homozygous deleterious alleles that are causing like degradation. So maybe after this I can send you that paper.
Okay, so that's good. I just wrote that down, and I do have some follow-up questions and some responses. I think we're just getting into the meat of it. I'm going to put this question up if you want to answer it. Take your time. I should have went to the restroom before. I drank a coffee. We went right into this. I should have went to the restroom before. Take your time. Answer this. I'll be back in 30 seconds, and then I've got a couple responses based on what you said.
Yeah, okay. So I would first ask, like, what do you think you would find in the fossil record. If you know, for the sake of argument, you accept that the population bottleneck happened, what would you be expecting to find in the fossil record? I mean, you would have a reduced number of individuals, so that's a reduced chance of leaving any archaeological trace behind. There could be, you know, depending on what caused this bottleneck, could be environmental factors. You might be, you know, expecting to see those in the rock strata. I know that there's a popular theory of the Mount Toba eruption causing this population bottleneck. And we certainly see evidence of the effects of that in the rock strata. But in terms of like what you would be expecting to see, you would be expecting to find a lack of, you know, remains, campsites, tools. You would be expecting to find a reduced number of those things in the rock strata if there really was a population bottleneck.
Okay. Back just in time. Okay, so I appreciate your answers there, Grayson. Now, they've done these experiments, as you've pointed out, with fruit flies, where they've been subjected to specific conditions that decreased heterozygosity, increased homozygosity. But after the fact, they increased resources, put them back into a healthier state, and essentially increased levels of heterozygosity. And what they discovered was very little to no homozygous deleterious alleles.
Yeah, the populations like healed over a few generations, getting back to like a healthy population number. The actual genomes, like the degradation of the genomes was reversed as well, just as like a result of the population expansion.
So an important question is, in these artificial environments, how many generations were these specimens subjected to of the inbreeding and then resultant increases in homozygosity?
Yeah, I couldn't give you a specific number. I mean, if we want to find the study, we can certainly do that on a subsequent one. But it was enough to where, you know, the genomes were in a degraded state.
So I think that would be the major question, and then therefore problem with this explanation is when looking at the hypothetical out of Africa bottleneck, it's not a 1 generation bottleneck. It's not even a 10 generation bottleneck. I mean, you need to have at least 1,000 years of inbreeding to reduce the necessary levels of heterozygosity.
Why?
Well, because if you have, and that's why I was asking you those questions about how long did you have, you know, erectus, let's say in Africa, how many out of Africa's, how many major bottleneck events, because
well, it just matters. It does. There could be one bottleneck happening very quickly that has the same effect. All it matters is who are the individuals left? How many of them are there? That's the only thing that matters in terms of like the genetic effects that we would see. It doesn't, like, you could have it be over 1 week and you could get the genetic effects. If it's wiping out enough of the population and there's only a small number left, then you're going to have all those same effects in a very condensed amount of time. It's just like it's a question of population size.
Well, according to your model, so today a prime example that we see is with the cheetahs. They're currently down to 7,000. They're incredibly inbred. Their sperm is degenerate. Conservationists are extremely worried about them. Okay. They've had a lot of deleterious alleles come to the forefront, basically. And so they've experienced a massive bottleneck. Well, how many cheetahs were there pre-bottleneck, and how long did they exist before entering a bottleneck and therefore getting to their current state? I don't know if you know the answer to that, but I would assume it's going to be more than a couple generations. Go ahead.
Yeah, but it only takes 1 generation. That's what I'm trying to say. Is like it just, you know, if you have a great dying off of like all the cheetahs, and then there are only a handful of cheetahs left, within 1 generation, you're going to see all of these effects. It doesn't have to take a long time.
So is it your position that the out of Africa bottleneck was 1 generation?
No. As I already stated my position, I'm not putting a time on it. I don't even have a guess.
Right. I would confidently argue that you're not going to find anybody that says it's 1, 2, 10, regardless of if the effects can happen in one generation. I'd argue no, because you have a highly heterozygous population that gets slammed for whatever reason. The population's reduced. Well, whatever you have in that population of, let's say, 2 to 10,000, the individuals themselves are not highly inbred and therefore manifesting the inbred effects right away. It's going to take generations of the inbreeding to manifest those effects, even if it is 10,000 people. Yeah, go ahead.
Yeah, I'm just saying, like, it's all a question of size, right? Like, this is why I brought up the peopling of the Americas example, because all of those people, like the Native Americans, are all very genetically similar. They're not very diverse, and they've had a long time, thousands of years to diversify. But it's because they started from a small population crossing the Bering Strait that, like, you have all of these effects. So, like, there was no great disaster that wiped them out or anything. That was a population expansion, but they started from a small number of individuals, and that's why we see the effect. It's all a question of the population size of the bottleneck. Like, the time frame doesn't really factor into, like, the results that we would see. That's why I said, one generation. I'm saying, like, mechanistically, this could all happen in a very quick amount of time. There's nothing, there's nothing that would prevent that from happening, other than, the fact that typically something that would wipe out a large number of humans is not just going to reverse itself in 1 week and all of a sudden the environment is great again. And it's like, oh, now there's all these resources for us. And even though last week there was like a huge dying off, that's why scientists are not sure about how long this would take, because it's like a question of, the environment and like, what was causing this die off versus, how long it would take the environment and the human population to recover from that. So I thought we were going to be talking about out of Africa more so than just the African bottleneck, because we haven't gotten to the actual out of Africa hypothesis yet. And I had some questions for you about that.
Yes. Okay. Let me sum it up in here. I think we got your answers. I think I understand your position. I would still argue that it's not feasible, simply because even the examples you're giving, there's a difference between, we can see this in the phylogenetic trees, in the mitochondrial DNA and the Y chromosome. We have a lot of people groups founded in these haplogroups, founded by just a few people, right? But when you have a few people, and then what follows is rapid and exponential population growth, and not 1,000 years where that people group stays small, stays isolated, and continues inbreeding, then yes, you're not going to have those damaging inbreeding related effects. But my main issue, and I think there's a lot of unknowns and a lot of I don't knows, and I'm not saying just with you, but in the literature, when you actually look into this, and again, I stand by my statement that this is post hoc ad hoc, because it wasn't predicted. They were caught off guard. They invoked the out of Africa population bottleneck. But again, what happens in a prolonged bottleneck, it wasn't a one generation bottleneck, is we have severe genetic damage, because you have massive numbers of these deleterious mutations that have been accumulating for millions of years in Australopithecine like ancestors up to habilis, up to erectus. Okay. And what you have in this small isolated population is these deleterious mutations now manifesting and becoming fixed. Okay. So the basic question is, and answer it again, however you feel best. And then we'll kind of move on from here and branch off to some of the more details in terms of the out of Africa scenario. So what I have written down is the fruit fly experiments, other experiments. Again, these, from my understanding, are not prolonged bottlenecks. They're not the same type that is put forth in the out of Africa population bottleneck. Okay. Also, small people groups that are rapidly expanding and then spreading out. That's not equivalent to the so-called out of Africa population bottleneck. The out of Africa population bottleneck is unique. And therefore, the question is, how could such a small, nearly extinct, genetically compromised population just suddenly explode into all parts of the globe, seizing dominion over the planet. We're sitting here talking over StreamYard. They've built the space shuttle, and basically we've come out of a near extinction event. We've got all these deleterious alleles popping up, becoming fixed. I just feel like there's a lot of storytelling there. I feel like there's a lot of unknowns, and too many unknowns to actually be considered a valid scientific hypothesis. So I did say a lot there, but I wanted to make sure to touch on everything that I've written down that you've said. And so go ahead and provide an answer, and then we'll kind of move on from here.
Yeah, okay. So you're basically asking the same thing that you've been asking, which I directed to the fruit fly study. People are like, oh no, like Grayson never comes with papers. It's like, okay, but I've read papers and I remember them, and you can Google them. But okay, here's a paper. I Googled it while we were talking. How are deleterious mutations purged? Drift versus non-random mating. There's one example of a paper for how deleterious mutations are purged out of populations. But yeah, I mean, it's not like I just have a file with all the papers I've ever read in my whole life on it.
Well, Grayson, if you
I
don't
just
mind,
print out papers all the time just in case Donny asks me a question. These discussions are not pre-planned that far in advance.
right.
It's not like I'm, I have a library behind me with every paper I've ever read just in case Donny happens to bring up a question that would be relevant to it. It's not like I've, these are months prepared, pre-planned statements. Anything that I said, I encourage people to fact check for themselves. Go on Google, find the papers. They're really easy to find. Like Google Scholar is your friend.
So the reason why I'm asking you, and I get what you see, genetic drift versus random mating, the fact that a lot of mutations are lost over time due to genetic drift, while a lot aren't. Lots still float around. But that, to me, is not really an answer to the question that I have asked several times. And I've asked several times because I don't believe in any of the debates that I've had. I've had 100 formal debates, most of them on these related topics. And currently, I don't think the evolutionists have a good answer as to how this hypothetical out of Africa population bottleneck is feasible in light of the severe inbreeding.
Right.
Again,
for the third time, look at the fruit fly paper. I mean, we're a broken record here because I say it, and then you bring up the same question when I'm saying the answers are like done in experiments. It's not just
how many but you've already said
notes.
Yeah, but you've already said you didn't know when I asked you how many generations was this.
You're asking a very specific question about
Well,
methodology,
that's
which I would explain the number of generations doesn't matter. But the main thing I want to get to, because
no, you're dodging. I need to let the audience understand. The main problem associated with this is it's not a one generation bottleneck. It's a prolonged bottleneck. So the fact that you're advancing a fruit fly experiment where you don't know how many generations this artificial population and this artificial environment were subject to, that's very telling. That means, no, you don't have an answer, because if it's not a prolonged bottleneck, many generations of inbreeding, I guess, going on in this experiment, then no, it's not equivalent. It's apples and oranges. The main problem with the out of Africa population bottleneck is the fact that it is prolonged, and it has to be prolonged in order to explain the necessary levels of genetic variation. And so we can agree to disagree, leave it up to the audience, but no, I don't think it's been adequately answered. I think it is a major problem for human evolution. And so, yeah, go ahead. Oh, are you on mute?
Yeah, I mean, I don't know what to say. You keep repeating the same thing over and over again, and it's not going anywhere. And
well,
it's kind of annoying.
and we can agree to disagree.
And everyone in the comments is like saying, "Oh, I didn't come out of Africa. I came out of the Middle East. I'm an Aryan." And like, that's what I was told we were going to be talking about, the out of Africa hypothesis. So
this is
for
the
our
out of
next
Africa
discussion, I will bring the papers you want. I will send them to you in advance. We can go over them and we can show the exact mechanisms, and we can go sentence by sentence on the methodology if that's what makes you happy. And we can go through all of these things for your audience. and we can show how these deleterious mutations are purged out of the population after experiencing a bottleneck that increases homozygosity with an increasing population that then makes the genome healthy again. We can show that. It's not just one experiment. It's multiple. Not just
because we haven't observed models. Well, we have an observed example today. Okay, firstly, you said you read my book, and you asked me before we did this, is this the out of Africa argument that you iterated in your book? And the answer is yes. I got a whole chapter on this. This is the main argument because this is out of Africa. And if there's no solution to this problem, dude, the population bottleneck occurred in Africa. Yeah. And if this population bottleneck's not feasible, then guess what? We didn't come out of Africa.
But none of that is the out of Africa hypothesis that was the subject of the talk.
The out of Africa hypothesis is false if you don't have an answer to the severe inbreeding problem that would have taken place.
The out of Africa hypothesis is false if abiogenesis never happened. Why aren't you asking me about abiogenesis, Donnie?
Okay, I want to make this point. Today we have an example of what inbreeding does with cheetahs. They've gone from 15,000 to 10,000 to 7,000. They're extremely inbred. They're not getting better. Their sperms degenerate. Conservationists are incredibly worried about them. We're not suddenly going to see this population of 7,000 cheetahs spread out into all parts of the globe, seizing dominion over the planet. But that's what you want us to believe. You want to say it's scientific to believe that somewhere between 70,000 and 200,000 years ago, some highly inbred, highly degenerated population of 2 to 10,000 that have just experienced a near extinction event where a great multitude of deleterious alleles have manifested and gone to fixation.
Time you're repeating the exact same talking points over and over and over.
It's not a talking point. What it is it's a real problem.
Out of Africa hypothesis.
Okay, so what we'll do is we'll move on from here. I don't want you getting overly stressed. I'm having fun here. So, okay, so we'll leave it up to the audience. The question's been asked. You've provided what you believe is a solution, and so we'll go from there, okay? So we'll have to agree to disagree.
Well, you asked an off-topic question, and I will come back with all the evidence, and we can go over it if you don't.
Not an off-topic question. It is the major problem in the out of Africa. Sorry.
It's not part of out of Africa.
Did you read my chapter on out of Africa?
It's over 100,000 years difference from out of Africa. It's
Did
totally
you read
different.
my chapter on out of Africa? Did you read my chapter on the out of Africa?
Yeah, I read it twice. I read it again today.
And did I not put forth this problem in the chapter quite heavily?
Yeah, you talked about the genetic diversity.
Okay. So I appreciate you answering those questions. That was fun. This is an important topic. We can reconvene on this specific issue a little bit later. Okay. So where would you, I'll leave it up to you now for the last portion of this specific podcast.
Okay. I'll prove out of Africa. Okay.
Sure. Yeah. Go ahead.
Fossil record, stone tools, genetic diversity, genetic heterozygosity. All of these things converge to show us that out of Africa is true. All of these things, for example, genetic diversity decreases by the number of miles of distance you are from Africa. Okay? Like, same thing with heterozygosity, same thing with mutational load, same thing with linkage disequilibrium. All of these things literally vary based on how far away you are from Africa. Okay? Like, that's the genetics prove that the human species originated in Africa. And if you go back to that slide, mitochondrial DNA also proves it, because all of the mitochondrial haploid groups that we're all a part of, right? You have a haploid group. I have a haploid group. Neither of us are African. Both of our mitochondrial haploid groups are subsets of the African L3 group. Okay, like this is well founded within genetics. We also have the amount of stone tools that are found in Africa cannot be fit within 5,000 years. There are so many stone tools, and we don't find this amount of stone tools in any other continent. The amount in Africa is just staggeringly huge, and it cannot be accounted for in 6,000 years.
Okay, so I appreciate those points. You did just kind of commit the shotgun fallacy where you brought up 6 or
Because we
7
have
points.
10 minutes left for the entire topic. Like, out of Africa is the topic. So we only have 10 minutes left of the discussion to actually...
We've been on topic the whole time, but my point is, which one of those do you want to tackle first? Because remember, this is more conversational
Let's go
style.
for the genetics.
We're not doing the formal debate where now I'm going to respond for 15 minutes. Let's go one by one. Which one? Levels of genetic diversity you want to do first? Okay. So levels of genetic diversity. Okay. So firstly, what we discussed for the first 45 minutes shows that the levels of genetic diversity are not in support of the out of Africa model. Okay. But firstly, your main issue is levels of diversity in Africa in general. I'm guessing autosomal DNA, mitochondrial DNA, Y chromosome. So here's the Y chromosome.
No, the issue is not the issue is not the level of genetic diversity in Africa. The issue is that the level of genetic diversity decreases with distance from Africa. That's the whole thing.
Actually, the epicenter of genetic variation worldwide is right around the Middle East region, where we would say,
nope.
Yes, no, it's a fact actually. And there's debate.
Where's your paper?
And there's debate. I can pull it up. But
yeah,
here, I want to address. Okay, just wait. I want to address your levels of genetic diversity, or the where the epicenter of diversity is that you say. Okay. So, firstly, I've got one paper here, if I could find it, that goes into let me see here. So this goes into what drives genetic landscapes. Okay. And in this paper, there's actually several papers on the issue. They describe drivers of genetic landscapes not necessarily being reflective of the age of a population, but actually having to do with mutation rates, which are variable among people groups, and also with what's called the PRDM9 enzyme and rates of recombination. So before I go on, are you familiar with the PRDM9 gene and how it affects recombination and how recombination affects genetic variation?
No. So, but what you're saying is that it's all a coincidence that the mutation rates and all of these different recombination factors all just happen to align such that we get genetic diversity in whatever direction you go from Africa. It decreases in that direction. So you're saying it's a massive coincidence.
It decreases from the Middle East. But right here,
where's your paper for that?
Well, it's mixed in with all these.
Well, we only have 5 minutes. That's the topic. Show me that paper.
Okay, I want to go over this specific paper.
No, I mean that's not the topic.
You're dodging. This Grayson, I'm not dodging because this is exactly
all Donnie.
You just said, Grayson, that you're not familiar with the PRDM9 gene, which actually addresses your problem here. So notice this. This isn't a creationist paper. Okay. It says, thus, the shorter extent of West African linkage disequilibrium is not due to differences in demographic history alone, such as the lack of an out of Africa founder event. Basically, it's saying when you look to levels of genetic diversity, there's a lot of replacements going on. We have people that are in people groups in Africa today that didn't actually originate there. We had originators in Africa, but they were completely replaced due to conquest, due to people groups coming in and replacing. Okay, so even if, for sake of argument, what you're saying is true, is that levels of genetic diversity decreased west, east, wherever you go in Africa, okay, that still doesn't help you. Because again, there's paper after paper here that talks about how genetic landscapes, levels of genetic diversity, and also your directions of where genetic diversity is going, if it's decreasing from a certain area, is not necessarily a reflection of age.
So you're saying it's all a coincidence then?
Well, it's not. Okay. Is that what this paper is saying? The landscape of recombination, or let's see here. PRDM9, driver of a genetic map.
Yeah, you're saying that the factors that affect PRDM9, okay, that those factors in Africa have to coincidentally create more genetic diversity in Africa, and then with the distance from Africa, right? So you have less genetic diversity in the Middle East. less in Asia, even less in the Americas. And you're saying that the PRDM9 factors that are affecting that are just coincidentally reproducing that pattern.
No, it's not coincidentally. It's just a fact that we have certain spots within the genome that are more hypervariable. We have the PRDM9 gene that's actually designed, Grayson, to look for a specific set of letters on the chromosome. What it does is it grabs onto it and then it recombines. It shut every generation you're having recombination where these
So
genetic
how does that
variants
explain the pattern that we see?
Well, because if you were to look, there's a number of papers here that goes over it. So let me explain it. Right here, PRDM9, a driver. Notice this, a driver of the genetic map. So if you have a genetic landscape of Africans versus non-Africans, okay?
Let's do the world.
Yeah, well, in the world overall, you have a lot of very large linkage blocks, which are sometimes 10,000 or more nucleotides that have actually experienced no recombination. You have these original text strings that you would expect to be more scrambled up.
You're dodging.
If we go back millions of years, okay? So here's the thing. PRDM9, a driver of the genetic map. Most, if not all, meiotic recombination events are controlled by the PRDM9. So if this is the case, which it is, there's paper after paper, okay? And we know that Africans have more of these sites. That's what this is saying. Notice this. There's an increased frequency of these PRDM9 genes in Africans. The large number of hotspots, read the paper, it's right on screen, available to West Africans implies that at the population level, crossovers are more evenly distributed than in Europeans. So we have more pieces of DNA in African populations.
But you're not explaining
evolutionists,
how you get a smooth gradient of genetic diversity decreasing with distance. It's a mathematical.
It doesn't matter because you have replacement populations, but the fact that you have more recombination genes and hotspots in Africans, that means you're going to have more potential. That means you're going to have more potential to harbor more genetic diversity.
Okay,
because these elements, listen, quit talking over me. I didn't talk over you and ask questions. We understand that these elements, these PRDM9 genes, they are drivers of genetic landscape. So yes, your Africans have more pieces of DNA. Okay, more evidence for recombination, and more recombination per generation, Grayson, means that population that's experiencing more recombination per generation, they are going to hold or retain more diversity.
So let me get this straight. You're saying that there's more recombination in Africa, and then there's slightly less recombination in the Middle East, and then there's slightly less recombination in Asia, and then there's slightly less in America in a smooth gradient. And you're saying that the PRDM9 explains that smooth gradient that
there's not as okay. You're saying that there's this perfect smooth gradient. Paper, cite it right now.
Sure, I've got it open. Distance from Africa, not climate, explains population phenotypic diversity in Africa. Linkage disequilibrium in human populations. Distance from sub-Saharan Africa predicts mutational load. Like literally all of these genetic factors are calculated in a gradient with distance from Africa. You can't just look at Africans versus non-African groups and get that gradient. You have to look at, how the distance factor is affecting these. And for your worldview, that has to be a complete coincidence.
Well, it's not. Okay. You just said in that paper, linkage disequilibrium. Yet this paper here, coming out of Nature, the landscape of recombination in African America, says, thus, the shorter extent of West African linkage disequilibrium is not due to differences in demographic history alone, because we have in African populations, firstly, they're closer to the equator. We have examples where DNA repair enzymes are damaged, leading to more mutations. We have in the secular literature, paper after paper. I mean, we could go to this one. The initial discovery of PRDM9's role in the recombination process, the location of recombination hotspots, where this element seeks a specific a set of letters on the chromosome and grabs onto it and recombines, leading to more diversity. There's more of these in Africans. All you need.
You're dodging. You're not explaining the gradient.
The gradient doesn't
you're
matter.
avoiding bringing up the question of the Middle East epicenter that I asked 15 minutes ago, that I told you were dodging on, and you said we were going to get to, and now you're going off on this whole topic about PRMD9 because you don't want to find the epicenter.
Okay. Firstly, you not understanding the answers that I'm providing you is actually your problem and not mine.
Oh, I'm understanding what you're saying.
No, you're obviously not, because you just read.
You want me to repeat it back to you?
Yeah, read the linkage disequilibrium part back to me in that paper.
No, I'm not going to read it. I'm going to repeat back to you what I'm saying, demonstrating that I have an understanding of what you're trying to get across. You're saying that within African populations, the PRDM9 activity is such that recombination events are higher, and thus the linkage equilibrium is higher. That's what you're explaining this. It doesn't explain the other people groups and how we see a gradient in genetic diversity and linkage disequilibrium. You're not explaining the gradient. You're just explaining why it's elevated in Africans. That's all you're doing.
The elevated amount of PRDM9 sites, mutation rates, and recombination hotspots means that African populations are going to be able to harbor and retain more levels of genetic diversity than populations outside of Africa.
That's literally what I just said.
Exactly. And that's answering your question.
No, it's
whether
not.
There is
My
this
question
smooth
is about
gradient or not.
Okay. You're not addressing the gradient. You continue to dodge. You are dodgeball Donnie right now. Answer the gradient.
The only one dodging is you. Okay. So, so right here, Middle East. Genetic diversity in the Middle East is very high, like you're saying.
You got no source on this page.
Northeast Africa is the center of genetic diversity. Genetic diversity goes down as you go west in Africa and as you go southward in Africa. That means the origin of humanity could be in the Middle East at the Tower of Babel. Okay. And
Sub-Saharan Africa has the highest genetic diversity.
And Northeast Africa being the center of genetic diversity. You're saying
you have no source for that. You just claimed it on a slide without listing a source. You told me
you can read all these sources that I'm showing you on screen that have to do with genetic landscapes.
You're not showing me a source on screen.
I've been showing you sources on screen the entire time.
You just showed me a claim about the epicenter of genetic diversity with no source attached. And
you can read this paper. Hey, listen,
you can read this paper. Source. You got your slides in front of you and no source.
Okay, refute what I'm saying. The fact that the origin of humanity could be in the Middle East based on the fact that genetic diversity goes down as you go west in Africa and as you go southward in Africa. The fact that Africans have more working PRDM9 sites, which is a fact, they have there's variable mutation rates, higher mutation rates in specific regions in African genes.
Source.
Okay. Ugh.
You're only talking about the HBB gene. You're talking about one gene. You're not talking about genome wide.
Listen, are you saying that because there's one gene that experiences hypermutation, are you going to go on record and say that's the only gene that experiences hypermutation?
I'm going to say that the mutation rates of the African genome
you asked
for
the source. Elevated. We also found that the overall point mutation rate is significantly higher in Africans than in Europeans in the HBB region studied. Is it your position that the HBB region is the only part of the genome in Africans that is subject to higher mutations? Is that your position?
No, that's a stupid, slippery little question, Mr. Dodgeball Donnie. No.
Well, listen again, Grayson. You not understanding why you're being refuted tonight is a you problem and not a me problem. Okay.
You haven't refuted anything I've said.
Okay. Firstly,
name one thing I've said that you've refuted. Name one.
Are you going to go on record right now and say that genetic diversity does not go down as you go west in Africa and as you go southward in Africa? Are you going on record and saying that point there is false?
The epicenter of genetic diversity is sub-Saharan Africa. That is what I will go on record saying.
Okay, so therefore you're going to go on record saying that Northeast Africa is not the center of genetic diversity.
Yeah, genetic diversity in the Middle East is not the epicenter. Northeast Africa, not the epicenter. Okay, like the epicenter is in sub-Saharan Africa, like Ethiopia region, that kind of general area of sub-Saharan Africa.
Okay, I want to write down your answers for our second podcast so I can make sure
all of this is recorded. You don't need to write it down.
Okay, so firstly, Northeast Africa being the center of genetic diversity, you disagree with. Do you disagree with Africans having more PRDM9 genes that act in recombination than non-Africans? You agree with that or disagree?
I'll agree with that. Who cares?
Okay. Do you believe that there have been waves after waves of migration into Africa resulting in replacements?
Yes.
You agree with that?
Yeah.
Okay. Do you agree that Africans have been subjected historically to faster mutation rates for a number of reasons?
Why would that be the case?
Well, firstly, being environmentally related. I've got papers here showing that environments can result in a faster mutation rate. And Africans are historically where? Closer to the equator.
But you also say Neanderthals have a higher mutation rate and they're not near the equator. So
Well, it doesn't there's different environmental factors. Neanderthals lived in harsh ice age related conditions where the clouds would block vitamin D from getting in. As a matter of fact, when they sequenced the Neanderthal genomes, they found massive rungs of homozygosity, showing that they actually showed a lot of degenerated genes and alleles in Neanderthal genetics. But yeah, their environments, their ice. So are you saying that ice age related conditions are not as bad as being close to the equator? I mean, they're both bad environments, but they're different. Doesn't mean that they're not bad, though. I don't know. What's your point there? Go ahead.
Yeah, my point is that mutation rates are not significantly different based on where you live. Like, I mean, unless you're living next to a nuclear reactor or something, like your mutation rate is going to be similar for most of the human population. Like, you're not going to have higher mutation rates in Africa. You're not going to have higher mutation rates in Northern Europe. Okay. Like, it's going to be very similar mutation rates.
Okay.
We don't observe. I mean, show me a paper that says Africans have higher mutation rates in their genomes. You've got one paper that they've got one single gene that has higher mutation rates. That, that doesn't prove jack.
Okay, so I guess this brings us back to our original debate, where you can literally manifest worldwide genetic variation on a phylogenetic tree, and you have differing size branches, indicating that people existing at the same time are picking up more mutations than each other. So people are picking up more mutations than their cousins in the same amount of time. You can see that clearly here in the HVR haplogroup. And then you're going to complain, oh, rooted versus unrooted. But here's the thing. The data doesn't change whether it's rooted or unrooted.
Do you know what a rooted tree of this data would look like?
Yeah, it'd be that stair-step looking tree where you
and where would
somewhere on the L.
Where would right around where your cursor
right
is.
here.
That's the center.
That's the evolutionary root, but that root is based on evolutionary assumptions, for example, assumptions on the molecular clock. But again, these variable mutation rates, what they mean is there's no evolutionary molecular clock.
You agree that nested hierarchies can be observed, right? You agree that, like, I mean, you say all the time that the creationist model predicts nested hierarchies, right?
Right.
So when we look at the mitochondrial DNA, we see that the entire left-hand portion of this, all of the different haplogroups that don't have an L in front of them, all nest within L3, okay? Which is an African haplogroup. Every single member in this audience right now,
you're nesting,
not African, has a haplotype nested within the L3 African haplogroup.
So you're saying I'm dodgeball Donnie when you just dodged harder than anybody I've ever seen dodge before. Again, everything you're saying is based on that root on the L node, which is about midway around here is where the evolutionists put it. And it's all based on DNA differences. It's all based on the size of the branches. It's all based on an ape to man evolutionary assumption. Those are all broken by the fact that we have variable mutation rates. And you can see this on this. I didn't make this up. Anybody can see that you have. So for example, all these branches here, where do they go back to? What's this? You see this branching pattern? This is a common ancestor. That means this female ancestor.
It's not. Unrooted
what?
trees do not show relationship like you're implying. Like you can't show that in an unrooted tree. It's the basics of a rooted versus an unrooted tree.
This is worldwide mitochondrial DNA diversity. Okay. So regardless of if it's rooted or unrooted, the fact that people are picking up more mutations in the same amount of time exists, whether you root it or not. Is it your position that if you root it, suddenly this doesn't exist? Is that your position?
No,
Yes or no?
my position is that when you root it, then and only then can you talk about the genetic relationships.
You get an ancestor to descendant relationship when you root it. Yes. But that
So
doesn't
why don't
change.
you root it?
Because rooting it requires many assumptions. Firstly, before I rant for 20 minutes, have you read this paper yet? If not, that's fine. You can read it for next time. An overview of the independent histories of the human. Have you read that? If not, that's fine. Have you read it though?
No.
Okay. So in that paper, Dr. Sanford and Carter spent an entire section, at least 2 pages, explaining where they could possibly root it from the young earth creationist starting point, and where we could possibly root it and where the evolutionists do root it from the evolutionary starting point. But they discuss exactly why that's problematic in light of what we actually see in the data. On top of the problems, the biggest problem is the variable mutation rates. Now, in these papers that we've looked at, the reason why mutation rates are variable are not fully understood, but they could be due to gene conversion, for example, which might have a correlation to levels of heterozygosity. They describe all this in the paper. Might have to do with environment, might have to do with defects in DNA repair enzymes, might have to do with the PRDM9 gene. Okay. And there's papers even in the secular literature trying to explain this type of stuff. So the data itself doesn't change. This is a natural reflection of the data. We still have the haplogroups. We know who the groups are: African line, European line. We know where, the Indian haplogroups are, Chinese haplogroups. That doesn't change. But you have to make an assumption based on where you put the root. And it is an assumption based on the number of mutations, diversity, a constant mutation rate, a constant clock. Go ahead. Is there anything I'm saying that you think is false?
Yeah, I mean, we can tell by looking at the genomes, like the genomic sequence, we can tell if something is more derived or more basal, right? You can tell if it's closer to the root of the tree or if it's farther from the root of the tree, like by this genetic sequence. Also, I feel like you accused me of dodging. I don't even know what question you said I was dodging, but then you proceed to just completely ignore what I said about everything nesting within L3.
Well, you're the one who started the accusations of dodging. But my point is, your argument, why it was a dodge, is because you ignored the fact that your argument is based on something I just refuted, which are the assumptions that go behind the rooting in the first place.
Name
And
one.
you can't explain the variable mutation. How do you explain the fact that this HVR haplogroup, most common in Europe, easy to understand, why do you have differing size branches going back to the same ancestor? How do you explain the same amount of
That
time?
chart does not show it's the same ancestor. I want to be very clear. You cannot get that information from this unrooted chart. That information cannot be gleaned. Okay, that's not how unrooted charts work. Okay, so
why don't you do this? Why don't you do this for next time then? Okay, go ahead.
These variable mutation rates that you're talking about have never been observed. Okay, it's not observed.
Okay, why don't you do this for us next time? Get a tree that's rooted where you think the root is. Okay. Get us a rooted tree that's not unrooted like this with the starburst pattern. And let's compare the unrooted tree versus the rooted tree that's based on your evolutionary assumptions. Okay. Because what you're saying now, we don't have the image itself to verify.
I can explain what you would see is that L0 would be the very first branch.
Right. And then you see a staircase pattern after that.
Yeah, that's what we would see. Like the L's come out first, and then
and everything is nesting within the L.
Everything is nesting within
L.
But
that doesn't change the date. That doesn't change the worldwide mitochondrial DNA diversity that we have that's plugged into a system, and that system spits out a rooted or an unrooted tree. In this case, it's an unrooted tree. Okay, so I guess you're just disagreeing with these branch lengths and
No, I'm
variable.
not disagreeing with the branch lengths. I'm saying those branch lengths represent not mutation rate, but time. Okay, like
Yeah, but
that's very
why do they
clear,
represent time?
huh?
Why do they represent time?
That's how these charts work. Like
No,
you could
I
construct this
know,
chart with a family group, and
but
and,
what
and you can
I'm,
see the same thing.
I'm saying, what about the line? What about the branches represents time?
The length of the lines,
I understand, but the length of the branches represents what?
time.
But what goes into the branches, the lengths? What's making them their specific sizes?
Time. That's what I keep saying. Why aren't you getting this?
Mutations.
No, like
Yes.
that's
Why do you think the L branch is the longest here? That's because the Africans have the most mutations. They have the most diversity.
the most mutations from what?
They have, when their genomes are sequenced, they have more diversity than your non-Africans, than, let's say, some of your Europeans.
No, you can look at that branch right there. What is that? The HVR branch? There's way more diversity in that branch.
Are you,
than there is
wait,
in the
are you
L0 branch.
actually disagreeing with the fact that these branches represent mutations, DNA differences?
DNA differences between the branches, yeah, but I'm not. It's like when you
DNA
say that
differences
there are
between
more
the people.
mutations in L0, more mutations compared to what?
Okay. Did you watch the Dr. Dan Stern Cardinal versus Nathaniel Jensen debate there, the impromptu debate from a few months ago?
I've seen clips.
Do you remember when Dr. Dan asked Dr. Jensen what the lines separating the different groups represent?
Okay, enlighten me.
And Dr. Nathaniel Jensen said DNA differences, and Dr. Dan said that's right. This isn't something to dispute. I mean, this is just a basic fact of phylogenetics.
Yeah, like if you have the different lines like L1 and L0, like that's the genetic differences.
Which branch reflects more mutations? This one here, let's say the African branch, or this branch over here in the European haplogroup, HVR?
Yeah, the answer is obvious. HVR.
No. I'm saying which one has more mutations?
Oh, the L0.
Right, but why?
Okay.
Because the branch is
Because
longer.
it's longer, more time has accrued for those
No,
mutations.
that's your problem. Is you're assuming because it's longer, and therefore it has more mutations, therefore it's older. That's your assumption. But again, if you have,
it would be very easy to disprove that assumption if you could show me that mitochondrial mutation rates vary based on these haplogroups. If you could show me that, then that would easily refute this assumption. But you can't because no one's ever measured it. It's not observable.
Okay, so firstly, we understand that Africans have more working PRDM9 sites, more
That doesn't
hotspots.
affect mitochondrial DNA. There's no recombination in mitochondrial DNA.
So your mitochondrial DNA specifically is reflected here in this phylogeny, and you have differing size branches. And we've already established that the size of the branch is the number of mutations. You can count up the differences. You can count up the differences in each branch that go back to a common ancestor. And so if you have differing size branches going back to a common ancestor, that means you have variable mutation rates. This is pretty basic. But nonetheless, if you disagree with that, we're the ones as creationists that are saying, okay, in light of all of these factors, we're going to look to some of these African people groups and we're going to predict. We are confident that they're, whether it's more generations, right? Maybe they're marrying at a younger age, 13 to 15, and therefore more generations have passed and therefore more mutations. Or maybe it's DNA repair enzyme related. Maybe it has to do with gene conversion, PRDM9 gene. Maybe it has to do with environment.
You see how this is just an ad hoc explanation for like data that conflicts with your worldview? I mean, this is the same thing that you accused the out of Africa theory of doing with the bottlenecks. You're just coming up, you're spitballing any possible explanation that you can think of that could possibly explain this observation.
So is it your position, yes or no, that everything I'm saying in terms of gene conversion, PRDM9, environment, DNA repair enzymes, is it your position that this is all unrealistic? This all doesn't mean faster mutation rates? Like, is that really your position?
It doesn't explain anything we're looking at in this chart with mitochondrial DNA.
Okay, so what would you predict then? Let's say in the Khoisan peoples, we haven't measured their mutation rate. It's not yet known. Would you predict, before we get the DNA, would you predict that it's the same? It's pretty constant with the rest of the human population? Or
Yeah.
would you, okay, so that would be your prediction. You'd put that on paper and not have a problem with that?
Yeah, duh.
Okay.
It's the same for every people group that we measure.
Again,
Geneson's never been able to find a people group that have a different mitochondrial mutation rate.
Well, I think it's very reasonable to say that if we have papers demonstrating hypermutation for various reasons, hypermutation in families today, if we have papers showing how PRDM9 drives genetic landscapes, we have papers showing that different regions experience faster mutation rates, I don't believe it's an extrapolation fallacy to therefore say that, hey, these groups that are affected with these environmental conditions I should say, or have more of these PRDM9 sites or have more rounds of gene conversion, I don't think it's an extrapolation fallacy to say, okay, therefore they're going to harbor more genetic diversity. I don't see that as being a problem, but I guess you do.
100% is, because everything that you're talking about does not apply to the mitochondrial DNA. You've never been able to demonstrate, no one has ever been able to demonstrate that the mutation rates within mitochondrial haplogroups are different. Show me any data that supports that.
Okay, so your migration waves into Africa, different people groups coming into Africa after Babel. We have different tribes and then interbreeding within the tribes with very little random mating. Okay, that could explain the diversity that we see easily. Okay, selective sweeps across Africa, which is very plausible, that could explain it. The inbreeding in these isolated tribes where you have these mutations popping up and then rapidly becoming fixed, we know per population genetics that's
so the inbreeding is what increased heterozygosity.
No, the inbreeding wouldn't increase heterozygosity, but
exactly.
But it would make that tribe more distinct from other tribes and then other groups from around the globe.
The genetic diversity within Africa is more than the genetic diversity outside of Africa.
Right, but if you have, I'm talking about your uniparentally inherited DNA compartments, like your mitochondrial DNA. Mm-hmm. Your mitochondrial DNA, you could have, like with the Neanderthals, if you have the founder of Neanderthal, let's say it's just a small family, they branch off early after the flood, or even according to your model, just a couple people branch off, which has been suggested, you would have a fully coalesced mitochondrial DNA chromosome, where everything that now accumulates and becomes fixed or makes that chromosome unique will be unique to any other mitochondrial chromosomes when compared. Do you understand that? If you have
but we wouldn't see it as being basal to those, like we do with L3 and like the L haplogroup, like which are definitively, like all the other haplogroups nest within them. Okay, you can't show that effect with higher mutation rates. It doesn't work. It would look different.
Okay, so it's your position. Let me write this down. It's your position that all of your haplogroups nest within the L haplogroup, which is in Africa, and everything nests from there. Everything is essentially nested in the African haplogroup, yep, because the African haplogroup's the oldest.
Yep. And specifically all of the haplogroups that are found outside of Africa all nest within specifically the L3 haplogroup.
The L3 haplogroup. But and what's the reasoning for this?
Because that's the genetic signature of the out of Africa. It was like the actual people that like were the ones that, migrated out of Africa, right, were L3 mitochondrial haplotypes.
But what about the genetic signature? What gives this? You're saying genetic signature, but what gives the? What about their genetics gives that signature?
The fact that all of the outside of Africa haplotypes are nested within the L3. That's the genetic signature.
But
Is
what
like that
makes them
nesting that we can observe.
right? But what results in that nesting?
The genetic sequence of the mitochondrial DNA.
But what about the mitochondrial DNA sequence makes every other haplogroup nest within it?
Okay, your DNA is nested within your ancestors' DNA. Okay, you're
Right.
derived from them. Okay, you can compare the sequences. If you don't know who's the parent and who's the child, you can tell which is which because one is nested within the other.
But my question is, to say that non-Africans nest within Africans, what about African versus non-African genetics give you that idea?
The sequence of their DNA.
What
Like,
does their sequence look like?
you want me to start listing A, C's, and T's? What are you
No,
asking?
just say, what about the sequence? Is it the level of diversity, the level of mutations? Is it the pieces of DNA that they have in their population? Because your arguments are circular. You're not really telling me. You're just saying, well, it's because of their genetics. And I'm asking you, well, what about their genetics? And then you're saying, well, because non-Africans nest within Africans. Well, why? Oh, because they're tell me what about their genetics?
So
What
you're
is it?
asking what about like comparing two sequences allows us to know which sequence nests within the other sequence?
So you're saying you take an African genetic sequence.
Yeah.
And then a non-African genetic sequence.
Two non-African genetic sequences.
Okay. And then, and what about the sequencing data tells you that one nests within the
Okay,
other?
so when you're looking at two non-African mitochondrial DNA, right, you can see the mutations that they have, and you can see the base pairs that they have in common with the African DNA, right? So you can very easily decipher the order of which these things nest based on, like, you know, if you have an A here, like an A and a T here, and you have a G and a T here, you know, like they both have a T in common, and then you have the common, like the African, like more basal sequence there, you can tell, oh, these two derived from this one based on their sequences, right? You compare them to each other and you say, okay, obviously these two, like one did not come from the other between these two. But you look at the parental strain and you can tell very easily, oh, these are nested within this one. They are derived from it. It's
so
like,
technically, what you're saying, and this kind of brings us back to the start of this portion 30 minutes ago, is people outside of Africa have less overall genetic variation than people inside Africa. And the observed DNA sequences outside of Africa have close relatives within Africa.
And it's the type of genetic variation that they have. Because you can tell, you see what they have in common and what they have different. Okay, so you do that with enough genetics, and they sort into nested hierarchies.
So you're saying that there's a component or an element of the genetic variation found inside of Africa that has no close relatives outside of Africa?
Yeah, the other haplotypes like L0, L1,
right.
You know.
Okay. And everything that I've explained thus far, okay, explains exactly why we have the unique differences. It explains the levels of genetic variation. It explains the pieces of DNA. Okay. And so rather than me reiterating all these things, let me ask you one question, then we're going to wind it down. Okay. If all of this is a major problem for us, why do we have still, in light of everything we've been talking about and all the pieces of DNA that you have floating around in African genetics versus outside of Africa? Okay. Why do we still have these large linkage blocks that exist in the human species, in the human genome, that have really no evidence for any recombination, any gene conversion, any scrambling? Why is that? If we go back to, let's say, 200,000 years in some out of Africa migration.
Are you asking like why there are areas of the genome that haven't undergone recent recombination?
Yeah, because if we've had 200,000 years of bottlenecks, a couple major bottlenecks, as you're saying, okay, but then every single generation we get recombination, gene conversion. People are probably like, why does he keep saying gene conversion? Gene conversion is similar to recombination, but the difference is there's evidence that it can swap single nucleotides, okay, rather than, you have the chromosomes line up and basically mixing with each other. You can have the swapping of single nucleotides. And there is some papers and some data that suggest that possibly if you have more heterozygosity, you're going to have more gene conversion. Okay, but that's up in the air. They're still studying that. But anyways, so if you're having every generation for 200,000 years, you're having recombination, gene conversion, you're having mutations. That's a lot of recombination, gene conversion. So why aren't the genomes, both Africans and non-Africans, how come they're not more scrambled? Why do we still have these large intact linkage blocks that essentially have no evidence for scrambling?
What part of the chromosome are those linkage blocks located in?
Those linkage blocks are located all throughout the genome, all throughout the autosomal DNA.
Yeah, but where in the chromosomes? Because there's certain areas like subtelomeric regions in chromosomes that are much more likely to undergo recombination. And then there's areas near the centromeres that have like almost 0% chance of undergoing recombination, because recombination is a three-dimensional physical process that occurs between chromosomes, right? So if you are in a spatial area of the chromosome that doesn't have a physical chance of undergoing recombination, you're not going to see that.
Okay, so in other words, you're saying there's cold spots and hot spots in terms of recombination within the human genome?
Recombination doesn't have an equal chance occurring at anywhere in the genome. It happens at some places more than others.
So there's been selected areas in the genome that have experienced recombination over the last 200,000 years, and other spots you could say are cold, and so they're not experiencing recombination.
Yeah, like subtelomeric regions undergo the most recombination events. Like the areas that are close to the ends of the chromosomes are undergoing recombination at a much higher rate than areas towards the center.
Yeah, that could probably result in some good predictions. That could probably be tested. Okay, so what I want to do is I'm going to take 2 minutes here, sum everything up. You're the guest. I appreciate you doing this. It gets a little heated once in a while, but it's fun. The audience likes this. I enjoy it. These are technical topics. They're needed. So I'm going to take exactly 2 minutes to sum everything up. Then you get the last 2 minutes though. Okay. So you can tell the audience how much I dodged and failed and, I need to retire and whatnot in your 2 minutes. Okay. So I'm going to start the 2 minutes and we're going to start it now. Okay. So I think this has been a good discussion, a good first episode in this, I'm sure, podcast. It'll get progressively more and more heated, but I like it. It's important. Okay. So the first 45 minutes had everything to do with out of Africa versus out of Middle East. Okay. We would suggest that actually there's slight background noise. Grace, if you could mute just for the 2 minutes. The Bible tells us that God created Adam and Eve just 6,000 years ago. Right off the bat, that restricts levels of genetic variation. What do we find today? Very low levels of genetic diversity. We're all 99.99999% the same. Low variation in the Y chromosome, the mitochondrial DNA. As a matter of fact, the Y chromosome and the mitochondrial DNA are nothing alike when compared to the chimpanzee uniparentally inherited DNA compartments. Okay. Well, this makes sense. Just 6,000 years ago, Adam and Eve are created. This restricts genetic diversity. What do we have today? Low genetic diversity. The evolutionary community and what Grayson is advocating for here is the out of Africa theory, but also the out of Africa bottleneck that is necessary. It's necessary in order to explain levels of genetic variation. So yes, the out of Africa population bottleneck problem that I would say is an unsolvable problem due to the subsequent inbreeding and the long-term nature of the bottleneck. Therefore, you have these recessive deleterious alleles coming to the forefront for probably thousands of years, according to their model. and they lead to rapid and accelerated genetic degeneration. Okay. This is an element within the out of Africa hypothesis. It needs to be discussed. So in my last 40 seconds, his major problem with the nesting of non-Africans within Africa, I've provided a number of explanations, one specifically with the PRDM9 enzyme. It's an amazingly complicated and well-designed DNA element that basically looks for a specific set of letters on the chromosome, grabs onto it, and then it recombines. Okay, and I've showed a number of papers here that PRDM9 sites and the hotspots associated with it, they are drivers of genetic landscapes. And so if you have a population like in Africa that has more of these genes, more working genes, and also more of these hotspots, they are going to be able to harbor more genetic diversity. Okay. And the last thing I'll say is when it comes to the phylogenetics, the variable mutation rates, okay, that can explain a lot of what we see in terms of the mitochondrial DNA and the Y chromosome. And Africa could have been founded by a population with more working PRDM9 sites. Here on the slide, waves of migration into Africa post-Babel can explain diversity differences. And I'd highly recommend reading through a lot of these papers that attempt to deal with these issues, okay, when it comes to selective sweeps, patriarchal drive we didn't even get into. But all of these things considered, I think very reasonably explains what we see in terms of African genetics versus non-African genetics. So actually that was 3 minutes. So if you want, Grayson, take 3 minutes and go ahead.
Yeah, I don't really have anything to say. I mean, you know, I was told that the topic was going to be out of Africa. Then we talked about bottlenecks for 40 minutes. We started an hour later than I was promised. And we went on for almost 40 minutes over time. So, you know, I mean, next time, you know, I'll bring papers about the topic at hand, I guess. But, you know, you could ask me all kinds of random questions, and I'm not going to have every single paper that's ever been written by everyone on the planet. Okay. And I'll post in the comments. Well, I guess YouTube doesn't let you post links, but I'll post the names of all the papers so that people can see, you know, not just making up the papers. Yeah, I mean, it's kind of a not that enjoyable of a debate, honestly.
Oh, that was a little shorter than 3 minutes, but I just got back. Okay, so Grayson, appreciate the very depressing closing there, but I appreciate you doing this, and take some time, look into these arguments a little bit, read over my book a couple more, maybe 20 more times. And to the audience, thanks for tuning in, even though it was very late. This was fun. Okay, with that being said, Standing for Truth is out. God bless.